Today I'm going to show you a use of the transformed area method in reinforced concrete design. Using the given working stresses and steel in concrete, we're going to find the uniformly distributed load, or the UDL, the beam can support in addition to its self-weight. The values are given as gamma C, which is the unit weight of concrete, is 0.15 kip per cubic foot. Allowable concrete stress is 1800 psi, which is FC, and Fs is the allowable steel stress is 24,000 psi. Length of the beam is 28 feet with a modular ratio of N equals 8. The beam is assumed cracked, so it is necessary to locate the neutral axis first. Once located, we'll be able to find the cracked moment of inertia of the beam and then other parameters to find out exactly how much this beam can support in addition to its self-weight. So let's draw somewhere the neutral axis first. Let's say this is below the box. So if we redraw this thing, then it's going to be something like this. Let's call this y as the distance to the neutral axis of the beam. Okay, so the equation that we have to write is the area moment above and below the neutral axis must be the same. Since the beam is cracked, we do not consider the uh, the contribution of the concrete below the neutral axis. Okay, so the equation will be, so the solution to this problem is 20 times y times y over 2, which is uh, the entire section minus the hollow section will be 8 times 8, and the centroid to the hollow section will be right here, and then that is going to be y minus 4 and 4, 8. That must be equal to the transformed area method. That means we are going to transform the area of steel to equivalent area of concrete. And we can do that by using N times AS. AS is the area of reinforcement or area of steel. So NAS this time will be is 8 and AS is 5 number 10. So 5 number 10, each one is 1.27 inches squared. And the distance to the center of the reinforcement is D minus Y, or D is 29 minus Y is unknown. We're going to find. This is assuming that the neutral axis is below the box. From there, we get Y equals 10.49 inch. But if you look carefully, that bottom of the box is 4 plus 8, 12 inch. So 10.4 inch, 49 inch is actually less than 12 inch. That means neutral axis is within the box. That means our first assumption was wrong. So we are going to um, find location of the neutral axis, assuming that the neutral axis is within the box. So let's do something. Let's clear this up. I think the stroke eraser will be a much better choice. Let's write down, draw the neutral axis right here, like this. So that's where the neutral axis is. And let's redraw this entire thing using black ink. That is All right, so let's do this. This time, assuming the neutral axis is within the box, the equation will be, this time we are going to split this area into three different areas. This solid portion, this solid portion, and this solid portion. So that is going to be 6 times y over 2, and there are two of them, plus the solid part right above the hollow box is 8 times 4, 8 times 4 times the distance from the neutral axis to the centroid of that solid part will be y minus 2, and that must be equal to NAS, which is again n is 8, AS is 5 number 10, 1.27 times 29 minus y. This gives us a value of y equals 10.53 inch. So that is actually the final value of distance to the neutral axis from the extreme compression fiber. Now we need to find the crack moment of inertia. So that is I cracked. We're going to take the entire solid section right above the neutral axis and then take off the hollow section. So this time moment of inertia will be bh cube over 3, or b is 20, and this time h cube here is 10.53 cube over 3 minus the hollow section will be, the width is 8, and the height of the hollow section will be 10.53 minus 4, which is 6.53 cube over 3. Now this is the area of concrete above the neutral axis. Below the neutral axis, like I said before, we do not include the concrete, only the reinforcement. So that will be NAS, which is 8 times 5 times 1.27, and the distance is squared, which is 80 squared. So distance is squared is 29 minus 10.53 squared. Don't forget the squared. That gives us a value of 24,371 inch 4. 24,371 inch power 4. That is the crack moment of inertia. Now we know this, the stress, the bending stress in any is M YC. For, let's say, for concrete, it will be MC YC, and I cracked. So from there, MC is FC I cracked over YC, or FC is given as 1800 psi times I cracked is 24,371. Okay, and then YC is the distance from the neutral axis to the extreme compression fiber, where this 1800 psi is allowed, and that distance is 10.53. Now this will come in pound and inch, so we divide by 12,000 to convert the pound to kip, and then 12 to convert the inch to foot. So that will give us 347 kip feet. 347 kip feet. Okay, now if we want to find the moment that can be applied due to the limit to the steel stress, so that way we can write the steel stress is basically N times the stress in concrete. So in terms of steel moment, and Y to the tension side all over I cracked. So okay, so MS, which is the moment due to limited steel stress, that is going to be FS I cracked, and N and YT. So that becomes FS is 24,000 times I cracked is 24371. Okay, N is 8 and YT is the distance from the neutral axis to the center of the steel, which is 29 minus 10.53. And now this is the value will come in pound and inch, so we just divide by 12,000 to get it in cubic feet. 330 cubic feet. Out of these two, the smaller one controls, and the smaller moment is 330 cubic feet. So that is the controlling moment. And we know moment in a simply supported beam is W L square over 8. Or from there we can find W is 8 M over L squared, or 8 times 30, sorry, 330. 330 over L square is 28 squared. So that gives you a W value of 3.37 kip per foot. Kip per foot. Self weight of the beam. Self weight of the beam is the total area will be 32 times 20 minus 8 times 8 is the whole over 144 times the unit weight of concrete is 0.15 kip per foot. So that gives us a value of 0.6 kip per foot. So the additional load that the beam can support will be 3.37 minus 0.6 is 2.77 kip per foot. Okay,